Okay, we have already lost 4 minutes extra for all these preparations and class 2 question 1. Let's look at the model that's given in this question. Actually, 8. Right, this model is estimated using a data set with 250 randomly selected males and 280 female workers. They're all randomly selected, and interestingly, this is 530 observations, right? A huge data set which improves our estimators' properties. Yeah, larger data set, the estimator in probability approach the true beta, true estimates. True value of this beta value. Well, this is actually beta 1 hat with an estimator, not the actual value, but yeah, this approach in probability in large samples to beta 1, actual beta 1 with the large sample, and our evidence will be much more reliable, I would say, attracts much more interest in the community and among the academia as well. Okay, let's look at this question. Says male is a binary variable that takes a value 1 if observation is male participant in the survey. Otherwise, it takes 0. Right? If an observation is a female, if the observation gender is a female, then this value the male variable takes a value 0. Do you understand how this works? Do you have it in your mind how this binary variables work? No. Usually, the data set that we have now here with the 530 observations is this. Basically, I'll just give you a quick kind of idea about what we're looking at. So let's assume that the first person, their wage, actual wage, we don't have the hat here, is let's say $7.40 per hour. And we call this next variable as a male, we name it a male, and let's assume that this person is a female. So then male takes 0. Second person earns £8 an hour, is also female. Third person, let's say, earns $7.90, and this is male. Then takes 1/4, 0/5, let's say 1/6, 1, so on and so forth. We have 530th observation, maybe let's say female. So 1 0 1 0 1 0. It alternates between 1 and 0. Right. That is this is our now in this model. This variable is independent variable, and wage is the dependent variable. And assume this is our spreadsheet. So we put it into Eviews and run regression, and this would be our result, predicted or estimated model. Now let's start looking at questions now. Have you tried doing the question 1? A. It says, what is the estimated gender gap? Guys, what do you think? What's the estimated gender gap? Let's take the average wages first of all for wage for female. What is it? It's basically 12.68 plus 2.79 times the variable male will now take 0 because it's a female. We're looking at the female average wage. This gives us $12.68 per hour. Let's now look at the wage male. Now times by 1, because now it's male, isn't it? So this would be $15.47 per hour. And gender gap is basically difference between the average wage of females and males. Well, it has to be the opposite because we don't want the negative sign. So it's basically 15.47 minus 12.68 gives us 2.79 pounds. This is the gender gap, average gender gap. And notice that this value, this is the same as this. So this estimated coefficient is actually a gender gap. So it's $2.79 is a gender gap. That's the answer to this question, and also answer to I think it's C as well, or D apparently. Yeah, D. Any question? Okay, next one then. Have you done the second one? Question B. B says, test the hypothesis that population beta is 0, alternative that population beta is not 0 with a two-sided alternative. Yeah, significance of the coefficient, gender gap basically, this beta 1. Now we usually do what? We estimate distance from 0. This value is how far away from 0 this value lies, because if it lies close to 0 then beta 1 is 0, so there is no gender gap. We need to test it using some probability levels. So we want to test it at 5% significance level. In that case, at a 5% significance level, the T critical value that we are interested in is usually 1.96, right? Because it's two-sided, you divide them by 2. So looking at the T value from standard normal cumulative distribution table for 0.0025. So we'll have a look at this later. Now for now, let's calculate the T actual, the actual T stat. And that is basically gender gap that we estimated minus 0 over the standard error of the regression coefficient estimate. And that is 0.84 given in the question. Yeah, 0.84 isn't it? Yep. And the T stat here is 3.32. 3.32. And let's look at how it looks. We won't draw this sort of curves later, but for class 1 and 2 I'll draw them to get the intuition right for you guys. Now we want to test how far or how close our coefficient estimate lies from 0. So in this case we converted everything to standardized form. In this we'll deal with T stats now, and this T value now let's say lies somewhere here and somewhere here. Because it's two-sided, I kind of mark two sides of this distribution. This will be 3.32 negative, this will be positive 3.32. Now the question is, how far is this from this distance? Or is it sufficiently different from 0? Now at 5% level, critical value is 1.96, so negative 1.96, positive 1.96. And we all know that T-stats that lie beyond this point and beyond this point would give us strong evidence that we have to reject the null hypothesis. And in this case, our T-stat lies beyond this point, beyond the critical value. And in this case, beyond this as well. So we look at the positive side, but because two-sided test, both is fine. Either one is fine for you. So T actual absolute value is greater than the T critical. Reject the null hypothesis. Essentially we're saying here is that there is a significant gender gap. Yeah, there is a significant gender gap. And this the coefficient estimate comes from a population with a non-zero mean. It comes from a population with a value close to this, maybe, close something. Maybe we create a construct a 95% confidence interval, and we'll have a look at what values it would take in 95% of the cases. Okay, that's reject null now. Next, it also asks us for p-value. What is p-value, by the way, guys? Anyone? It's basically area under this curve marked in red, sorry, yellow, or is it orange? Orange apparently, sorry. So we need to sum these two areas under the curve. This will be our p-value now. How do we get the probability values? The p-value is, by definition, is the probability of obtaining an or observing a t-stat that is as high as 3.32, and we usually look it up in the cumulative distribution function. In this case, standard normal. So I opened it earlier, and here it is. Remember, we had the 3.32, and whether it's negative or positive, it's all fine, because by symmetry they have the same probability of occurrence. Minus 32, minus 3.32 or plus is fine. So I'll just use the negative side. It will give me the same answer. So minus 3.32. So this, I have the minus 3.3 here. I just need to add the 2. So I go right under the 2, and this is the p-value for one side. This is for one side. So now our p-value, sorry, is equal to this is t stat, t actual, t stat, t actual, the same thing. And because we only looked up one side, I'll tell you what it is in a minute. It was 0.0005, right? Because we looked at one side only, which is this side here. It gives us this value, this probability. So the area under this curve here is basically 0.005. But we have the second side, so you times it by 2. And the p-value is less than alpha. Remember the alpha. What was it? Alpha was 0.05, right? 5%. Basically, alpha is this area under the curve. And our p-value is less than alpha. So we reject the null hypothesis. That's the second way of looking at the hypothesis tests.
So can you go back to the first method?
First method?
Using
What is method?
T actual is bigger than T critical.
Oh, you mean by looking at the t's?
What is the T critical again? Is it 1.96?
Yeah. It's 1.96 for 5%.
So 1.96.
Okay, let me have a look. Let's go back. You see this standard normal distribution. Let's go to 1.96. 19. Okay, 19, yeah? 1.9, go to the 6, just under 6. This is the one, isn't it? Or is it not? Okay, it's this one. 0.06 column. And, yeah, this is the value. You see? 0.025. This is one side. If you add this together, we have 5% with the positive side. So it's 5% level significance. And the 1.96 comes from this table basically. And probability of obtaining a critical value or a value as high as 1.96 is basically 0.025. And remember, we're testing at 5% level. And we split it by 2 because two-sided. And this was giving us 2%, 2.5%. T critical corresponding to 2.5% is 1.96 here. Yeah, that's where this thing comes from. But I assumed you had it in econometrics 1, so we are not looking at it. And we compare this against the T statistic that we obtained, and then we decide based on whether critical value is, T star is greater than or smaller than the critical. Is that clear?
Yep.
Yeah. Okay. And basically, area here, this area here under the curve, and this area here under the curve is 5% when you sum them. And these critical values are basically the boundaries of this marking. And this area here and this area here, when you sum, they are p-values. You compare p-value and alpha That's the second way. Yeah, is that clear? I mean, these things must have been much clearer by now. And anyway, okay.
Sorry, excuse me.
Yeah.
If p-value is smaller than the alpha value, and then what do we do?
You reject the null hypothesis.
Oh.
Yeah, like t value, t stat being greater than
Oh.
t critical then, isn't it? It's exactly the same. It's just one coin with two sides, but you read it differently on the t side with the t test and then with the p value. Slightly different, but it's the same thing. Is that clear now?
Yeah.
I'm recording this in case you want to watch it again or learn about it again. Go back to this again on YouTube. It will be on YouTube by Friday, this Friday.
What's your YouTube channel name?
Just type ECN225. It will take you there, and you'll see my channel. It's London PhD, but if you search for because you can't search channel names.
You can.
Can you?
Yeah.
Does it? I never done it, but usually I will search for videos. Okay, if it does, then it's better to memorize ECN225 than London PhD. Yeah. Okay, next. Construct a 95% confidence interval for the gender gap. Do you know how to do that? Because I want to skip it. Maybe I'll do it quickly. I have to rewrite everything. I just cleared. Now, this as this standard error. 95% confidence interval. That's a 95% confidence interval. You know how to interpret this, I guess. Yes. Yes, no? Yep, good. Okay, next. This was our, C. Now D, the answer for the D, question D, is already given in question A. When we answered question A, we worked out average wages. Remember? Average wage for females was 12.47 minus 0. Average wage for males was 12.47, sorry, plus 2.79. We just plugged in the values for male variable. 15 point, what was it? 47. So what is this then? Is this not 47? 68, sorry guys, this is 68. Yeah. Now E. Trying to be quick, guys. Without the class, we couldn't manage to do much of it. E. So population model for this task is given by this equation, and another researcher basically decided to record the binary variable by giving a value 1 if a person is female, a 0 otherwise. So far we've been working with the binary variable which takes 1 if a person is male. So she was doing the opposite. Most likely it was a woman, isn't it? Giving a female observation Female responded a value of 1, otherwise 0. Right, so we can rewrite this male as a function of female in this form. Yeah, if a female is if male takes a value 0, then when person is female, then this would be 0, so male will be 1, right? So use this by plugging into this to work out slightly different model. And wage this is our new population model. And when you run the regression, you should get something like this. And this is an estimator. Beta 0 hat is a new estimator for beta 0 plus beta 1. And this is the original estimator. So beta 1 hat is an estimator for this beta 1 now. Now let's use the coefficient estimates from here and plug in values in there to see what the coefficient estimates look like. So for this here, we plug in 12.68 plus beta 1, 2.79 plus 2.79. By the way, this is minus now. Female. So you have a new equation, estimate, using the sample, and it will be now if female takes a value 1 now, you get average value for female, which is the original 12.68. If a female variable takes a 0 value, then you still get the male wage, which is the same as before. And what is interesting is that you will have the R squared, which is the same again as before. SER will be the same as well. That's because we didn't change the data, did we? We still have the same observations. We still have the same people. 260 of them are 250 of them are males and 280 are females. And whether you run by changing the code differently on the data for the binary variable or not will be the same estimate. You're dealing with the same data, so R squared won't change, SER will change. Is that clear? All we did here is this. Now with this new model, female will take 1 instead of 0. In the original, female was taking 0 and male was taking 1, right? This is one coin with different opposite side. Okay, if you don't have a question, number 2. Consider a model yi beta 1 xi minus ui and find or estimate beta 1 to so that the sum of squared residuals are minimum, or by minimizing the sum of squared residuals we have to estimate beta 1 or find an estimator basically that minimizes sum of squared residuals. And remember, sum of squared residuals was this, right? So we need to minimize. We need to find beta 1 or estimator beta 1 that minimizes this value. So let's define a function s of beta 1, which is basically written as this. Instead of ui, yeah, I replace it with basically these values. Ui is equal to yi minus beta 1 xi, yeah, from this equation. And to find the beta 1 that minimizes the sum of squared residuals, take the first order derivative with respect to beta 1. Now in this case we treat beta 1 as an unknown, not the y and not the x's. These are given data, they are given to us, but we need to find this, a value for this that minimizes sum of squared residuals. And from your mathematics classes you know that you need to take derivatives, partial derivatives with respect to the unknown to find the value that would minimize this function. And let's do that. So take derivative with respect to unknown, then you get 2 yi minus beta 1 xi times minus xi. Yeah, chain rule. And if you equate to this 0, you'll be able to find, if you equate this equation to 0, you'll be able to find the beta 1 that minimizes this function. And let's do that. If you equate this to 0, then you should get something like this. And once you equate it to 0, this will be hat. Now it's an estimator. Because beta 1 hat could be anything. Once you equate it to 0, we usually denote the estimators as hats with the hats. Yeah, you can put the beta 1 star if you want, but the convention is beta 1 hat with a hat. Estimators are with hats. And I want to divide both sides of this equation by -2 because there's minus here, so it comes out of this thing, and all we get is a simple equation now. Now we'll deal with that now. We'll just work with that. What are we going to do with the summation operator here? Leave it for now? And what about xi? Can we multiply it in to the bracket? Yeah? No? Yes? Yes, we can. Now what? Anyone? We can't expand it because it runs from 1 to n. I runs from 1 to n, and you have n equations. God knows how many equations are there. Basically 530 for each observation. Yeah, n is equal to 530. So you would have a massive equation with just one unknown. Unknown is this. But notice that this summation operator is indexed by I, and all of these have i's. So why don't we just expand it by letting in the summation operator and attaching it to each of the expressions to simplify it, to make our lives easy. I let the beta 1 hat to be outside the summation operator because it's a constant, isn't it? It's an unknown value that takes one value. It is not indexed by I. Yeah, it's not indexed by I. It's 1, beta 1. So it can be out. And if I solve this equation for beta 1 hat, I get something like this. And this would be our solution. That's our estimator. If you have yi and xi and x, just take the product and sum them up across i's and divide it by squared x's, sum of squared x's. And this gives us the beta 1 hat. Actually, n is not related to this, obviously. It's the second question, but then for some reason I thought of first question. Yeah, there were 530 observations. It could be infinitely many. That's the answer. Okay, number 3. There's a video. I won't spend time on this. I'll go number 4. Yeah, I have the video for number 3. If we start number 4, we'll be finishing it just in time. Eviews exercise now. So can you switch on your computers and download the data from QM Plus? It's not WebCT, it's just from an old system, I think. This is from my other class that we were talking, so the previous estimates. Can you download the file called collegedistance.xls, open it in Eviews, and you should be able to see this data view like I have here, work file. And after this, please read the question. Is everyone ready? Ready? No? No? Yes? Do you need help? Okay, we start now. We're running out of time, guys. So if you read the question, it says, run a regression of years of completed education on distance to the nearest college. Report the estimated regression with the standard errors, R squared and ACR. Now, distance, the variable dist is proximity to college. Maybe it's the number of miles. It's measured in miles. You need to read the definitions of variables available from QM Plus again. I do not remember it, to be honest. But the education is number of years in a college. So it's the relationship that we're looking at is, yeah. So let me go. So we're looking at the relationship between the distance between the high school and the four-year college and the, what's this, education, number of years. For the first question, click quick, estimate equation, and a simple regression model with ED, dependent variable, type ED. Independent variable is dist, and C is the constant, intercept. We could hit OK now, but we would like to make sure that standard errors of coefficients are robust to heteroscedasticity present in the errors. So we go to options and choose, in the covariance method option, choose Huber-White and OK. Go back to specification if you want or not. OK. So idea here is to see if distance has an effect on education. years completed. Now, we need to report standard errors. Standard errors are here. For each coefficient estimate, standard error is given. And also coefficient estimates are given here. For distance, it's 0.07 with a minus sign. And if you take the distance coefficient and divide it by standard error of that coefficient, it gives you the t statistic, the one that we've been calculating. Yes? And t statistic is larger than minus 1.96 in absolute value. So probability value is then has to be less than 0.05. This is which is the case here. So that's one point. Second point, r squared. This is a tiny, tiny, tiny value, right? And do you remember what r squared was? It's coefficient of determination? Measure of fit, yes. So how would you write in a test if it asks you to comment on the r squared? How would you write? What do you put in the test? Okay, yes. So basically, the 0.07% of variation in education is explained by variation in distance. Only a tiny fraction, right? It may tell you something about missing variables. So remaining 99.003% is explained by other variables which we didn't include. So essentially, this tells you something about omitted variable bias in the estimated equation coefficient. So this is a biased estimate. This could change if we add more variables. But anyway, now look at the standard error of regression, 1.8. Keep this in mind. It won't tell you much now. But when we reestimate the model and then compare it against the new model, you will see the difference. It should go down if our new model is better than this one. And also, I expect r squared to go up, and this one to change as well, up or down. We'll see how it goes. But as of now, given this, so this is the answer to the question B now. Given the values, if I divide coefficient estimate by standard error, it gives me t statistic 5.46. This is much greater than 1% value of 2.58. So I reject the null hypothesis of no effect on education of distance. In fact, there is a significant effect of distance on education. So how would you interpret this in context? In this context, how would you comment on this coefficient? Just like I did for r squared, can you do it for this coefficient? What are your comments, guys? Anyone? So basically, let me rewrite this model for you. Okay, I must have minimized it. Now, basically, we have ED hat 13.94 minus 0.07 dist. So how would you interpret this result? This is rewritten in context. What's the interpretation? Comment. What comment would you give? Yeah, there's a negative relationship. That's good. So in context, how would you say something about it? Am I confusing you? Maybe I thought it's the easiest thing to do.
Can you say like if the dist change by 1, and then there will be a smaller than proportionate change in the
Okay, you could say that as well, but that's quite detailed otherwise. So let's look at this. An increase in the distance to college reduces, if it's increased by a unit, it reduces the number of years in education by 0.07 years. Yeah, education is in number of years of high school. Now assume that between your high school and college, distance is 0. They are next to each other. How many years of education would you complete? Almost 14 years, isn't it? So the person leaving to high school, next to high school, and then the college at the same time, basically will have 14 years of education. So right after school, they go to college. But if your high school is here, and then your college is 10 miles away, it's a bit distance, isn't it, to drive and walk. So you might decide not to go to college. Something like this. This is a big decision, isn't it? Yeah, this is what we are looking at now. Distance between the high school and the, yeah. Obviously, you have to go to high school for the primary education, but then for the college, it's a big decision, and you decide depending on distance and other factors. But we are now looking at the distance as one factor, and it is not a very big amount. I mean, it's not offering a big amount of variation, exponential variation in education, but it's actually significant impact, has a significant effect, yeah, on its own individually by looking at t-stat and p-values. Now, question D now. I'll skip 95% confidence interval. It's an easy one, right? Or maybe I'll do it quickly. Let's do it very quickly. Let's look at the confidence interval, 95% confidence interval for this coefficient estimate. For that, you go to view, go to coefficient diagnostics, confidence intervals. And in there you will see three values, 0.9, 0.95, 0.99. Delete the ones that are not 95. So keep the 95 only. 0.95. And click OK. Now, here you see your original coefficient estimates. These are called point estimates. And this is your confidence interval for distance coefficient. The effect of distance could be as high as 0.09 or as low as 0.047. 95% of the cases, yeah? Or you have 95% confidence, that's an easy one to write, yeah? Done for C. Now D, we need to be quick now. D says, run the regression with education and distance by adding more factors that could explain number of years of education. Not only distance, but everything else, or some other things. Click estimate for that. You see this bar, estimate, click, and after this, just after this, type next variable, which is by test. This is from your problem set. Female, so we are also looking at gender, if it has impact on the decision to go to high school or not, college or not. Black, so we're looking at race as well, Hispanics. White is dropped variable, so it's not there. Income high, you know, rich people can afford colleges and can drive longer. You know, can spend on college trips easily. Own home. We're also looking at whether having a home or living in a rented property or in your own home will be an effect as well. That college, that call, it's also about, you know, we're looking at whether if students that has a college degree or not, and what's the effect on education, their education. Yeah, you know, imagine a guy with an engineering degree, they would, you know, encourage their kids to go to college even if it's far. Yeah, or imagine a tailor who works at home and does the things without a degree. You know, they have their own business. They would actually encourage the kids to be with them, help them. Yeah, sort of thing. So let's see if that's the present. That sort of effect is present. CUE 80, it's something from 80s. I need to read. I mean, you'll have a look at this. I mean, watch the video when you come back to this. Watch the video alongside the definitions of these. That's a long one. This one is very long. FG, again, 80s, something from before. And leave the C as it is. We want the thing to be there, the intercept. Click OK now, or just hit enter. Hispanic is not defined, so I might have misspelled. Yeah, Hispanic. It's Hispanic. Yep. Interesting result, isn't it? Look, what we have first of all, every single coefficient estimate is statistically significant at 5% level. So everything is important. We'll keep them in there. Another thing is, notice coefficient estimate for distance now is 0.01, sorry, 3 with a negative, so minus sign. It is an evidence of presence of omitted variable bias. Yeah. So our new estimate, this one, this new equation is better than the first one. So we stick to this one. That's because look at R squared. It's now 0.27 up from 0.007. Much large explanatory power. Yeah, this model has a much large explanatory power. In other words, 28% of variation now is explained by the model, by the variables jointly. And also, remember I told you to keep an eye on standard error of regression. It's now 1.54, and we had what we had earlier. I don't have it for some reason. It was 1.8, I think. The original SER was 1.8, so it's going down. So there's an evidence of presence of omitted variables bias in our original estimate, 0.07. So we now use this estimate, to investigate the effect of distance on college education. Oh, sorry, schooling, number of years in school completed. Is that clear, guys? And another question is, notice that the R squared and adjusted R squared are more or less the same. Why do you think it's so? Why are they the same? We expect adjusted R squared to be lower, isn't it? Or don't we? It should be lower, isn't it? But it's not here. That's because we have a very large data set. Yeah, if your data set is low, you get a difference. Low number of observations, I mean, small data set, then your R squared will be different from adjusted R squared, and adjusted R squared will be lower. But because of large data set, we have this sort of more or less the same adjusted R squared. Now, how would you interpret this result, guys? If you want to comment on distance coefficient, and if test asks you comment on the coefficient estimate of distance, so how would you do that in context? No one? No volunteers? Okay, now because we're dealing with multiple variables here, not just single, we have to hold everything else constant. It's a partial effect we're looking at now. So basically, this is what you write. On average, it's expected that the effect of, or average effect of distance on education is 0.03, holding everything else constant. In other words, an increase in distance by a mile, let's say, by a unit, reduces the college number of years of education by 0.03 years. Yeah. Further you leave from the college, or further your high school is from college, or the lower the number of years of education. Is that clear? Yes, no? No, yes, guys? Anyone? Or if you have a better definition, say it, please. Comments. The expected average effect of distance on education is 3.3. In other words, if a value of distance increased by a unit, number of years of education declines by 0.03 years, holding everything else constant. Yeah, the other factors are held constant. We don't change them. We just keep them as they are. There are better ways of writing it if you are good at English. Your English skills are better. Language skills are better. Okay, any questions? No? Now, question 3 answer will be online. I think it's already online from last year, so have a look. But this whole entire thing will be uploaded. Hopefully, will be, yeah. I hope that the sound didn't cut off. Sorry, say it again? It gets confusing as we go. So, watch this before you come and get prepared for this classes, every class.
Where's the register?
Register, I don't have it, guys. Where's the register, guys?